Alright, so since those were wrong on the video, I just copied again. I just copied the problem instead of what the answer was. Okay, these are the correct answers for 21. And if y'all want to, we can go over a couple like 21. Now, the other ones here, 1 through 19, we really shouldn't have any problems with that. Okay, let's just do this for those problems. Let's just review here. What do I do with an ordered pair when I reflect it across blank? Okay, so let's just start. All right, what happens to the ordered pair when I reflect it across y? Right, change sign of x. All right, when I reflect across y, then we change sign of x. If I reflect across x, then we change the sign of y. Okay, all right, what about the line y equals x? What would look like this? All right, yes, switch x and y. And then y equals negative x. Yeah, right. Switch x and y and change the signs. All right, what have I missed? The origin. What do we do there?
So,
change both signs, right. Okay. Now remember this. The origin is a combination of reflecting across the y and the x. That'll come in today's lesson. So when we reflect across y, we change x. When we reflect across x, we change y. So we change both when we reflect across the origin. Okay? All right. So now on 21, on A, B, C, D, and E here, do we need to go over? This is usually kind of difficult for some people. You want me to go over D? Okay. All right. So let me look at the problem and read it real quick here. All right, the direction said, find the image of negative 4, 3. Okay, so this is D. All right, negative 4, 3. Under a reflection in which one did you say? Oh, D. Okay, so that was 1, 3. Okay, so let's kind of visualize it here. We're going to take negative 4, 3 and reflect it across the point 1, 3. So visually it kind of looks like this. I take this point and I reflect across this point. So now this point over here is unknown. Now what was the significance about this point right here? It's the midpoint. Okay, so what we can use here is we can use the midpoint formula to actually find this point. But the only thing is we're not really using the midpoint formula to find the midpoint. We're using it to find the endpoint. So let's look at our midpoint formulas. All right, x equal x1 plus x2 over 2. And then y equals y1 plus y2 over 2. All right, so let's start with this one. So here's the thing you really have to buy into with these problems. This number right here, we know what it is. We know what the midpoint is. All right, so let's see if you can think about it. All right, Matthew, what number would this be right here? 1. Right. Okay, and then, all right, what number would this be right here? Negative 4. Okay. Now this is kind of a trick question, but what number would this be? We don't know. Right. So the x. Right. Okay. And then over 2. Now all we have to do to figure it out is solve this equation. Okay. So to solve it, to undo division by 2, we'll multiply by 2. 1 times 2 is 2. And then they just cancel out right there for me. And so we get negative 2 equals negative 4 plus x. And we just add 4 on both sides. And so that's 6. Okay. Now let's get our y coordinate over here. Now there's a shortcut here with the y coordinate, and I'll show you when we're done. Okay. But let's just take it normal first. All right. So what's our y coordinate of the midpoint here? I'm going to use, 3. Okay. And my first endpoint is 3. My second endpoint, I don't know. All right, over 2. Now let's just solve it. We're going to multiply both sides by 2. So 2 times 3 is 6. These 2's would cancel. Now I'm going to subtract 3 on both sides. So we get y equals 3. So our missing point here is 6, 3. Right, now, let's see if you notice a pattern there. If they have like the same y coordinate or the same x coordinate, then the third point is going to be the same also. Does that make sense there? Because they didn't change, did it? Okay, so it went 3, 3, 3. All right, so there's a shortcut that you really wouldn't have to really do this part of that problem. Okay. All right, we can look at maybe one more if y'all want to, or probably don't need to. That's fine too. Okay, y'all have another one you want to look at? Okay. All right, pretty good. Now, let's continue here with the idea of symmetry. Okay, now we're going to extend it to graphs of functions here, and what we're going to talk about are even and odd functions. And I'm just going to use my notes last period here. Okay. Let me get a better cover. All right. So even and odd functions. Now, the thing is, there's two approaches. There's the graphic approach, where we're talking about the graph of the function, or the algebraic approach, where we're talking about the function itself, like f of x equals x plus 2. We're looking at the algebra. Okay. Now, and what this deals with, to tell if a function is even or odd, it's really about the symmetry when we're talking about the graphs. So let's just look at the graphs. Okay. So if I'm looking at the graph of an even function, even functions are, Stormy, remember this? Nope. Okay, fine. Are symmetric, and I abbreviate this word a lot in this unit, with respect to, is what that means, the y-axis. Okay, even functions are symmetric with respect to the y-axis. Now, odd functions usually kind of mess people up a little bit sometimes. Okay, and they're odd are a little bit more difficult to identify. Thank you. Okay, so if somebody would guess, they would probably guess what here about odd functions. Symmetric to the x-axis. All right, why don't you think about that? I'm going to draw a graph here. That's not correct. Odd functions are not symmetric with the x-axis. Let me show you why. Okay, I'm going to take like a curve right here. Okay, now, if I was to take that curve and do a graph that was symmetric with the x-axis, we would flip this down and it would look like this, wouldn't it? Okay, well, what's wrong with that? It's not a function. So, we talked about, if we reflected something across the x-axis, this would be true. Functions are never symmetric with the x-axis because they wouldn't be functions. You'll see why it wouldn't be a function, right? Wouldn't pass your vertical line test, okay? So it's not like you think, all right? So here's the deal. Odd functions are symmetric with respect to the origin, okay? Not the x-axis. So the way I remember this kind of help me here is, I think, odd origin. Okay, double O. 7. No, double O. Okay, double alt buck. Here we go. Okay. Now, so let's look. Let's think about some easy ones that we know. All right. So, for instance, y equals x squared. Okay, what does that graph look like? I'm sorry. Odd functions are symmetric with respect to the origin. Okay. All right, so let's look at this one. Now, if we didn't know anything about even and odd functions, let me give you a hint. It's all about the exponents for the most part. So you'd probably guess that this would be even, right? Now, what does the graph of y equal x squared look like? It's a parabola, right? Going up, and the vertex is at the origin. Now, can y'all see the symmetry with the y-axis? See what I'm talking about? It's symmetric with the y-axis. If I take it and I flip it across the y-axis, then it would line up on itself. Okay, so that's what we're talking about with the graph, more so than this over here. Now, let's look. I'm going to look at about 5 graphs here with you. And let me show you especially like strategies on odd functions, because the even functions are pretty easy to tell, but seeing symmetry with the origin with the odd functions aren't as easy here. Okay, so let me just look through these graphs with you. All right, so A here. All right, let's look. Now, let's start off, and usually a strategy here to do is to take like one quadrant of the graph. Just look at one quadrant. So in this case, to me, what strikes me is the second quadrant right here, right? Okay. Now, if this is an even function, then we would see an image of this curve. What if it was symmetric with y? It would flop over here to the first quadrant, wouldn't it? So do y'all see a mirror image over here in the first quadrant? No. So obviously this one's not even. That's pretty easy to tell. Now, odd functions, on the other hand, are kind of difficult. Okay? So what I want you to think about with symmetry with the origin is this. Remember, symmetry with the origin is the combination of symmetry with the y-axis and the x-axis. Okay? Now, imagine what would it look like here if we did reflect this across the y and the x. So if I reflected it across the y, it would look something like this. And if I reflected it across x, would it land on this right here? Y'all see that? So y'all see how this is symmetric with the origin here? Okay. So since it's symmetric with the origin here, then we would say that this would be an odd function. Okay. Now let's look at B. B is a little bit different. Okay. Now, what about even here? No, it's not even. Okay. I think everybody can see that. Now, let's see if we can say that it's odd. Okay. So if it's odd, that means I could be able to take a piece of it and reflect it across y and x. Not necessarily in that order. Okay. You can do it in what order that you want with. Now, in this one, I'm going to choose this curve right here in the first quadrant. All right. Because it's not symmetric with the y. Right, if it was symmetric with the y, let's take this piece right here. If it was even, you would see a mirror image on this side over here. Okay? Now, let's go ahead and look at this. So, if I do reflect it across y and x, that means it's symmetric with the origin. So, that's reflecting it across y. Now, if I reflect this reflection across x, this is like 3 or 4 units above, so the reflection would be 3 or 4 units below, and you would get an image like this. Now, is that the same as that image? It doesn't flop on top of itself, does it? Okay? So guess what we say about this one then? It's neither. Really and truly, most functions are not even or odd. Most of them are neither. Okay? Now, let me show you something here and tell you a little bit about calculus. In these two graphs, this point and this point are called inflections points. That means it's a change in concavity. It's a change of curvature of the curve. Now, if that inflection point is at the origin, then it's probably going to be symmetric with the origin. Okay? So imagine this. If I took this, if this point was at the origin, then it would work. Can y'all kind of see that? All right. Now, let's look at C. Let's move on here. All right, so what do y'all think? Even. Can y'all see the symmetry? I'm going to take it here and just flip it across. All right. Let's look at D. D is a little bit more complicated. Okay. Now, it's definitely not even, is it? All right, so I think it's odd. I think you're right here. Now let's look at it and let's analyze it, okay? So again, I'm just going to take like one section of the graph. So the section of the graph that I'm going to look at is just this. Okay? Now, if I take that and reflect it across y and x, if I reflect it across y, it's going to look something like this. And then if I reflect it across x, it would land on top of that piece of that graph, right? So that is odd. Okay? All right, what about e now? Is that even? No. Even, you would have a piece over here, wouldn't you? Okay? Now, so if I took this piece and reflected it over here and then reflected it down, it would land on top of that one. Okay? So this would be odd. Now, what's something that you could do to that line that would throw it off and not make it odd anymore? Right. If you moved it down a little bit. So for instance, let's look at a graph like that. Okay? So let's think about odd functions. You really have to see something with the origin. If I moved it down, then you wouldn't have any symmetry anymore. Okay? Now, let me give you guys some graphs now. And we'll give you a ton of these because you can go through really, really fast and just name even or odd. Okay? Since I'm like tied to the thing here. Would you pass these out for me? Hand me one real quick. Just one. Alright. I'm going to start you off and we're going to look at like the first 2 or 3 of them. And what I try to do on this is I try to give you a lot of odd ones because odd ones are a little bit harder to identify. Okay? And I think, the more you can see odd functions, the more you'll just visually see them. And one thing about this is really, really spatial people, they see this like that. It's so easy if you're spatial, but if you're not spatial, odd functions can be a little bit challenging on the graph. Okay? And usually spatial people tend to be more males. And, females aren't as spatial. Like my wife, myself, I always know where north, south, east, and west is. I can go anywhere and I practically know where that is. Now, my wife, on the other hand, no. Okay? But she can do this. She's visual. I can ask her, where's my shoes? I saw them in the bathroom. She knows where they're at. Okay? Me, no. That's the difference between a man and a woman. Okay? And men are more spatial. And women have like super duper memories, especially bad ones, Okay. Hey, remember that time? Yeah, I know. All right. Let's look. See, I never remember that kind of stuff. And it's like, oh, I remember that now. I should have said that. All right. I think 1 and 2 are really easy. Let's just skip to 3 real quick, and I'll let you go back and do 1 and 2. Okay. All right. So let me see what y'all think about number 3. It's neither. Okay. So let's look. Now, do y'all need some help seeing that? Yeah. Okay. So let's look. Can you tell it's definitely not even? Okay. So it's the odd question. All right. So let's do this. Let's take like a piece of it right here. All right. Clearly it's in the first quadrant. So if it's odd, that means we would have reflected it across y and x. Now in this one I'm not even going to draw it because if I reflected across y and x, it would go from the first quadrant to the third, wouldn't it? Do you see anything in the third? No. Okay. So if it would have been odd, we would have seen, you take this piece, and then we would have seen something like this down there. Okay, and then there's nothing. All right, so that's definitely neat. All right, let's look at number 4. This one, number 4 is kind of challenging. Okay, let's see what you think about this. What is that? Starts at 0, goes up. Sine curve. Very good. Okay. Cosine starts at 1 and goes down. Okay. It's trig talk. You wouldn't understand. Okay. This is a sine curve. She's had trig, so she knows. Yeah, shift it over a little bit, and then it's a cosine curve. All right, now, let's look. All right, so what do y'all think? Even here? All right, so could I take it and like reflect it across? All right, you think it's odd? Okay, you're right. Now let's actually visually show it here. Okay, so if you're not sure, you remember you just take one piece of the graph. Okay, so I'm going to take this piece. All right. Now, if I reflect it across y, it would look like this, right? And then if I took this piece, would my pencil piece here reflect down on the actual piece of the graph? Yes. Okay. Now it looks like a camel. So it's odd. Okay. Now, are y'all starting to see a little bit better with symmetry with the origin now? Okay. The more you see, the better you get at. Now, let's look at 5, and then I'm going to let y'all finish. Go ahead.
Would it make a difference if the curved part on the bottom was at the top, or would it still be higher?
If that curved part was at the top, it would be even. Okay? All right. No, you start with a piece in any quadrant. Just whatever kind of looks better for you. All right? Now, let's look at 5.
Yeah.
All right. Here's the problem with even. All right. When you see this, if you reflect this piece, you get this down here, but then do you have this big old honking piece over here? It's neither. See, if this would have been even, you would have seen something like that, right? Okay. Now, all right, I'm going to let y'all go through the rest. So all you have to do is just write even, odd, or neither. Do the rest of them all the way up to number 24. When you get to 24, stop, okay? All right, 1 and 2 are both even. All right, and we did 3, 4, 5, and 6. All right, or did we do 6? 6 was odd, just in case we didn't do it. All right, 7 was, we said neither. Okay, so on 7, if you took the inflection point right here and moved it down right there, then it would have been odd. Okay, so if I reflect it, here's the reflection across the y, and the reflection across the x. This is 2 units above, so the reflection's 2 units below, or 1 unit below. It would look like this. It wouldn't match up exactly with that piece. Okay. All right. Number 8 was even. All right. 9 is neither. 10 is even. All right. 11. This one's a little challenging. That's odd. Very good. Are y'all starting to see odd functions really well now? And just the more you see them, the better you can really recognize them. All right. 12 is odd. 13 is odd. 14, neither. Yeah, 14 is kind of like 7. Right. So what you need for this one, your inflection point is like right here. If this was, again, if that was at the origin, it would have been odd. All right, 15 was odd. Okay, if y'all need some explanation, y'all say something. I'll go. Which one? Yeah, 15 is odd. Let me show you. Okay, so let's do this. Let's take this piece and let's reflect it over y first, okay? So I'm going to get something like that. Those are asymptotes, right? Now, if I took my red reflected curve, would it reflect on top of this down here? Yeah. Okay. All right. Number 16. All right, yeah, neither. Okay. Oh, what's the deal? It's not zooming on my computer, though. That's weird. Okay. It's like zooming on a smartboard, not the computer. All right, 17 would be, it kind of looks like a mustache. All right, 18 would be odd. 19 is odd. Okay. 16 was neither. All right, 20 was odd. 21, odd. All right, 22 would be even. 23 is even. 24, neither. Okay. All right, now let's talk about it algebraically here. And let me, hang on just a second. Now, algebraically here, I'm not as good at spotting them algebraically here as I am graphically. Again, that's probably because I'm a man, all right? But let's look at them. All right, so algebraically with even and odd functions, all right? If a function is even, so say I have a function f of x, okay? If it's even, that means f of x is going to be equal to f of negative x. Now, that notation is kind of confusing. I remember seeing that for like the first time, and I was in college when I saw this, and that really confused me. I didn't understand that, okay? So let me try to explain what we mean here. F of x is equal to f of negative x. And let me do that with an example. Okay? So let's say we got a function f of x equals x squared. Okay? Now, we know that's going to be even because we know what the graph looks like, right? Parabola, and it's going to be symmetric with the y-axis. Okay? Now, we have to figure out here, well, what is f of negative x? So if I was going to find f of negative x, that means that we're going to put a negative x in place of x. Okay? But if I put, see there's f of negative x, if I put a negative in place of x right there and square it, it's still going to be x squared. Okay? So notice, f of x and f of negative x would be equivalent, aren't they? It's the same thing. So because f of x equals f of negative x, that means that that function would be even. Okay, and we can think of it graphically there too. Okay, now, here's another trick too. All right, if we are looking at it algebraically, and we honestly don't know if it's going to be even or odd, it would be great if we had some kind of device that would show us the graph of it, right? Yeah. So we could graph it on a graphing calculator if we weren't sure, right? It would be a good way to tell. All right. Now, let's look at odd functions algebraically, okay? So when we look at an odd function, this is what has to happen with an odd function. For a function f of x, f of negative x has to be equivalent to the opposite of f of x. Okay, again, that function notation is confusing. All right, so just go with me, okay? Let's look at an example. Let's say that we're given a function, and the function's like 3x to the 5th plus 2x. Now, first, let's do this. What we need to show that it's odd is to show that this is true, that f of negative x is equal to the opposite of f of x. So let's find out, what would f of negative x be? Now, I want y'all to think about this. F of negative x means we're going to take negative x and put it in place of x here. Now, if this is being raised to the 5th power, which is an odd power, will it stay the same like it did on the last one? No. It's going to change the 3 to a negative. Okay, so this would be negative 3x to the 5th. Now, would it change this one too? So it would be minus 2x. Now, if this was 2x squared, it wouldn't change it, would it? Because when we raise a negative to an even power, it just stays the same. Okay, so now let's look at this. You can definitely tell these two expressions are not equivalent, are they? They're not equal. So what does it mean here? What's the significance that this and this aren't the same? Right, it's not even. Okay? Because if f of x is equivalent to f of negative x, it means that they're even. So obviously they are not the same. Now, this means the opposite of f of x. Okay? So the opposite of f of x means we do this. We're going to take the function now, not f of negative x, but the original function, okay? Not this one, but this one. The opposite of f of x means I'm going to take a negative and basically just change every sign or distribute a negative. So no matter what kind of exponents I have or what kind of constants, I'm just going to go through and change the sign of every number. So this would now be negative 3x to the fifth minus 2x. Now, right. So are these two equivalent now? Yes. So that means the function would be odd. Okay? Now, in just a minute here, I'm going to show you some really, really brief little statements that will clear this up, and you won't actually have to show all the algebra. Okay? You won't really have to show much work. We'll just figure out something. Now, so did you notice a pattern with the words even and odd here? Okay? So this is an odd function. What's odd in this problem? The exponents. So odd exponents tend to make me think that a function would be odd. And even exponents would think maybe a function would be even. Now that's not always true. There's an exception to that. And the way I'm going to show you that is with a graph. Okay? And it deals with constants. Okay? So let's look at some graphs just a minute. All right, let's look at the graph of x squared. All right, think about it and we'll change it. Y equal x squared again is a parabola, right? Now, so that would be a nice even function, wouldn't it? We just talked about that. Now, what if we did x squared plus 3? What would that do to the graph? You move it up 3, so it would look like this, wouldn't it? Okay, now, would it still be symmetric with the y-axis? Yes. Okay, so if I see a bunch of even exponents and I'm adding or subtracting a constant, adding or subtracting a constant doesn't affect the symmetry of an even function. Now let's look at an odd function though. Now this one we don't have as much experience with. This graph here, x cubed. Okay, we'll talk about it on Monday a little bit more. But now, when I look at the graph of x cubed, this is that snake-looking graph, something like that. And so it's symmetric with the origin, so it's an odd function. Well, it makes sense because this is an odd exponent. Now, even though we don't have much experience with the graph, we should know if I say x cubed plus 3, that's going to move it up 3 in it. Okay, so go 1, 2, 3, and so that inflection point moves from here to here. So now, is it still symmetric with the origin? No. Okay, so what happens is, this is basically what will happen. If you have a bunch of even exponents, it's going to be even. Okay, even if it has a constant. If you have a bunch of odd exponents, as long as you don't have the constant, then it's going to be odd. But you throw in the constant, it's not going to be odd anymore, it's going to be neither. Now, the only thing that I'm missing to tell you here is if you have both even and odd exponents, then it's neither. Okay? Now, let me show you a little summary of that. That way you can like write it down, and I think it'll really make sense to you here, okay? All right. So here's just a really, really good summary. Instead of showing all the algebra, if you just know this, then you can pick out even or odd functions. Okay? So even functions, this is algebraically here, okay? So this is opposed to saying f of x equals f of negative x. Okay? Even though I still want you to know that, okay? You just don't have to show it, but f of x is equal to f of negative x. Okay? That's what it means. Now, what that translates to is this. All the exponents have to be even. And it's perfectly okay to throw in a constant. You want to throw a constant at the end, like plus 3, minus 7. Okay. Now, with odd functions, almost the same thing. Okay. What all odd exponents. And now, what about constants? Constants don't work here, do they? So constants are not okay there. Now, what was the algebra behind it? When we say that f of negative x has to equal opposite of f of x. And when we get to the trig part, we kind of focus on these two things more so, because trig, you don't really have even and odd exponents. You have sine, cosine, tangent, cotangent, cosecant. All right. Now, let's do this. I'm going to let you look at these. Try to cover them up there. All right. And let's just go through and see what we think here. All right. So I need to really figure out a way to cover up the answer. There we go. All right. All right. So let's neither. Very good. All right. Let's talk about why it's neither. No, it's not really the 7. You have even and odd exponents. Okay. Can have both. All right. Now, what about even? Okay. You have even exponents. It has a constant, but then that's okay. All right. What about all right, it's going to be odd. It has all odd exponents. All right, and that's a 3. And it doesn't have a constant, does it? Now, if I throw in a constant, it wouldn't be odd. Right? That one's odd. Okay. All right, what about that one? Neither, because you have what, odd and even. Okay. All right, what about that one? That would be odd. Still odd. Still odd. Now, I scratched it out. If I put in a plus 7 or plus 10 or something, then it wouldn't be either. Neither. Okay. All right. Y'all kind of get the pattern now with these, so you don't really have to show all the algebra when you say odd or even. All right. Now look at the ones on the last part of today's stuff. Okay. 25 through 32. All right. Y'all go through real quick here. Take like 2 minutes and call them even or odd. All right, let's go through them. Okay, now haul them out here. 25, odd. All right, 26, neither. All right, 27, even. Yeah. Odd. 27 would be even. All right, it has an even exponent, right? The constant's okay. Just think about it. It's just going to take the parabola and shift it down 10. It's not going to affect the symmetry with the y-axis. Okay? All right, 28, odd. All right, 29, neither. Okay, the plus 10 messed it up. All right, 30 would be even. All right, 31, odd. All right, 32, neither. All right, for homework, nothing. Okay.